Somewhere in the darkness of space, a clock is ticking slower than any clock on Earth. Not because it is broken, not because someone is playing a trick on you. It is ticking slower because of something far stranger, something built directly into the architecture of the universe. If you dropped that clock toward a black hole and watched it through a telescope from a safe distance, you would see its hands slow down second by second as it fell. Not because the clock is malfunctioning, but because time itself in that region of space is running differently than it does for you. And here is the part that should stop you cold. From the point of view of someone falling with that clock, nothing strange happens at all. Their heartbeat feels normal. Their thoughts move at their usual pace. To them, time is just time. So which one is real? Is time actually slowing down, or is it an illusion, a trick of perspective? The answer, according to more than a century of experiments, telescopes, and equations, is both, and understanding why will force you to give up one of the deepest assumptions you have ever made about reality. The idea that time ticks at the same rate everywhere, for everyone, all the time. This is the story of how we found out that time bends. And it starts, like so many revolutions in physics, with a man staring at a beam of light and asking a question that seemed almost childish. Why this question matters for most of human history, time was treated as something outside the universe. A silent, invisible river flowing at the same speed everywhere, indifferent to stars, planets, or people. Isaac Newton wrote it into the foundations of physics itself. Time, he said, flows equably, the same for a falling apple as for a distant star. That idea worked. It built bridges, launched cannonballs accurately, and sent ships across oceans using nothing but clocks and stars. For 200 years, nobody had a serious reason to question it. Then, in the early 20th century, a series of quiet, careful thought experiments cracked that assumption wide open. And the crack didn't come from some exotic corner of the universe. It came from something as simple as a beam of light. Today, we know that time is not a river flowing the same for everyone. It is more like terrain, something that bends, stretches, and warps depending on where you stand and how fast you move. Near a black hole, that warping becomes so extreme that time itself seems to grind almost to a halt. This isn't science fiction. It is one of the most rigorously tested ideas in physics, confirmed by atomic clocks flown on airplanes, satellites orbiting Earth, and, most dramatically, the first ever image of a black hole's shadow captured in 2019. To understand why gravity can do this to time, we have to go back to a patent clerk in Switzerland who couldn't stop thinking about light. The historical journey, how we discovered time could bend, a strange fact about light. In the late 1800s, physicists believed light traveled through an invisible medium called the luminiferous ether, much like sound travels through air. If that were true, Earth's motion through the ether should change the measured speed of light depending on direction, like a swimmer moving faster with the current than against it. In 1887, physicists Albert Michelson and Edward Morley built an extraordinarily precise instrument to detect this difference. They found nothing. No matter which direction they measured, the speed of light stayed exactly the same. This should not have been possible under Newtonian physics. And for nearly 2 decades, it remained one of the most puzzling unsolved problems in science. Einstein's radical answer. In 1905, a 26-year-old Albert Einstein proposed something audacious. The speed of light is not the thing that changes. Instead, space and time themselves change to keep the speed of light constant for every observer. This became his special theory of relativity. One of its consequences was time dilation. A moving clock ticks slower, as measured by someone who is stationary. Not because the clock is broken, but because time itself passes differently depending on your motion. It was strange, it was counterintuitive, and it was correct, later confirmed by experiments with fast-moving particles and eventually atomic clocks flown around the world. But Einstein wasn't finished. Special relativity only dealt with objects moving at constant speeds. Gravity, the force that keeps your feet on the ground and holds planets in orbit, was still a mystery, the idea that changed everything. In 1907, Einstein had what he later called the happiest thought of my life. He imagined a person falling freely, like a skydiver before their parachute opens. In that moment of free fall, the person would feel weightless, as if gravity had vanished entirely. From this simple thought, Einstein built the equivalence principle. The effects of gravity are indistinguishable from the effects of acceleration. Being pulled down by gravity and being pushed by acceleration feel exactly the same. It took Einstein another 8 years of grueling mathematical work, filled with failed attempts and dead ends, to turn that simple insight into a complete theory. In 1915, he finally published General Relativity. The idea that gravity is not a force pulling objects together, but the curvature of space and time itself, caused by mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, and anything rolling nearby curves toward it, not because the ball is reaching out and grabbing it, but because the sheet itself is bent. Now imagine that sheet is not just space, but space and time fused together into a single fabric physicists call space-time. Massive objects don't just bend space, they bend time too, and the more mass packed into a smaller space, the more severely that fabric warps, until in the most extreme case imaginable, it doesn't just bend, it tears. Schwarzschild's impossible solution. Just weeks after Einstein published his equations while serving on the Russian front during World War I, German physicist Karl Schwarzschild found an exact mathematical solution to them. His solution described what would happen to spacetime around a perfectly spherical mass. Buried inside that solution was something disturbing, a boundary, a point of no return, where the curvature of spacetime became so extreme that not even light could escape. Schwarzschild had accidentally described what we now call a black hole, decades before anyone believed such an object could actually exist. For nearly 50 years, most physicists, including Einstein himself, considered this boundary a mathematical curiosity, a strange feature of the equations, not a real physical possibility. It took the work of later physicists, including Roger Penrose, to prove that black holes were not just mathematically possible, but a natural and unavoidable consequence of gravity under the right conditions. In 1965, Penrose published a landmark proof showing that once a star collapses past a certain point, nothing, no known force in physics, can stop it from forming a singularity, a boundary beyond which our current laws of physics break down. This work would eventually earn him the Nobel Prize in Physics in 2020. Black holes had gone from a mathematical oddity to an inevitable prediction of nature. The core science, why gravity bends time. Time as a physical thing here is the idea that takes the longest to truly sink in. Time is not just a number on a clock. In general relativity, time is a physical dimension, woven together with the 3 dimensions of space into a single 4-dimensional fabric. And just like space can be stretched and curved by mass, so can time. Think of it this way. Imagine space-time as a vast, flexible fabric. Far away from any massive object, the fabric is flat and clocks tick at their normal rate. But near a massive object, a planet, a star, or especially a black hole, the fabric curves inward like a heavy weight pressing into a trampoline. A clock sitting deep in that curve has to climb out of a steeper slope just to keep pace with a clock far away. It takes more effort, more energy to tick at the same apparent rate. And the result is that, compared to a distant observer, the clock in the deeper curve appears to run slow. This is gravitational time dilation, and it is not a trick of perception. It is a real measurable difference in how much time passes. An everyday example. You've already lived. You don't need to travel into space to experience gravitational time dilation. It's happening to you right now. Clocks at sea level tick very slightly slower than clocks on a mountaintop because sea level is deeper in Earth's gravitational curve. The difference is tiny, about 90 microseconds per year, but it has been measured directly using ultra-precise atomic clocks. In fact, this effect is so real that it has to be corrected for constantly in a piece of technology sitting in your pocket right now. GPS. Satellites orbiting Earth experience weaker gravity than we do on the surface, so their onboard clocks tick faster, by about 45 microseconds per day due to gravity. But those same satellites are moving at high speed, which, thanks to special relativity, slows their clocks down by about 7 microseconds per day. The net effect is that GPS clocks run about 38 microseconds per day faster than clocks on Earth's surface. That sounds insignificant, but because GPS relies on precise timing to calculate your location using the speed of light, an uncorrected error of 38 microseconds per day would cause GPS positions to drift by about 10 kilometers every single day. Without accounting for time dilation, GPS would be useless within hours. Every time you use a map app to find a coffee shop, you are relying on Einstein's century-old prediction about bending time, falling toward a black hole. Now take that same effect and turn it up to its most extreme possible setting, a black hole. A black hole's gravity is so intense that it curves space-time not just steeply but almost infinitely, near a boundary called the event horizon, the point beyond which nothing, not even light, can escape. Imagine 2 astronauts. One, named Elena, stays in a spaceship at a safe distance. The other, named Marcus, decides to fall toward the black hole, sending a radio signal back to Elena's ship every second according to his own clock. At first, Elena receives Marcus's signals once per second, just as expected. But as Marcus falls closer to the event horizon, something strange begins to happen. The gaps between his signals start to stretch. 1 second, then 1.5, then 2, then 5. From Elena's perspective, Marcus appears to be moving in slow motion, like a video buffering endlessly. His voice, if she could hear it, would stretch into a low, deep drone. His image would grow dimmer and redder as the light waves themselves get stretched by the extreme curvature of space-time, an effect called gravitational redshift. As Marcus approaches the event horizon, Elena would need to wait longer and longer between each of his signals. Mathematically, she would need to wait forever to see him actually cross the boundary. From her point of view, Marcus never quite finishes falling in. He fades from view, frozen at the edge, for all eternity, but Marcus experiences something completely different. The view from inside the fall. For Marcus, nothing about his own time feels unusual. His heartbeat, his thoughts, the second hand on his own wristwatch, all of it proceeds normally. As far as his own experience is concerned, he crosses the event horizon in a perfectly ordinary way, feeling nothing special at that exact boundary. This is one of the most mind-bending consequences of general relativity. Time dilation is not something you feel from the inside. It's something that appears when 2 different observers, experiencing different amounts of gravity, compare their clocks. There is no universal now. There is no single correct rate at which time flows. Time is relative to the observer, and near a black hole, that relativity becomes so extreme that two people can experience the same event as happening at completely different moments, or in Elena's case, never happening at all. Why extreme gravity, not just any gravity? It's worth pausing to ask, why does it take something as extreme as a black hole to make this effect so dramatic? The answer lies in how steep the curve in spacetime becomes. Earth bends spacetime, but gently, like a bowling ball resting on a thick, stiff mattress. A black hole, especially near its event horizon, bends spacetime so sharply that it's more like a bowling ball punching through a paper-thin sheet, creating a curve so steep it approaches a vertical drop. The closer you get to that drop, the more effort it takes for time to keep pace with someone farther away. Until right at the event horizon itself, the mathematics says that an infinite amount of distant time would need to pass for a single moment to occur at the boundary. This is not a flaw in the theory. It's one of general relativity's most carefully verified predictions, tested not just with satellites and clocks, but far more dramatically, using the light and behavior of matter falling into real black holes observed by telescopes. The scientific debate, where certainty ends. General relativity's predictions about time dilation outside the event horizon are extraordinarily well tested. But once you cross that boundary into the interior of a black hole, the picture becomes far less certain. The singularity problem. According to the pure mathematics of general relativity, all the matter that falls into a black hole is eventually crushed into a single point of infinite density called a singularity, a place where space, time, and the equations of physics themselves break down. Most physicists, including Roger Penrose and Stephen Hawking, who together developed foundational theorems about singularities in the 1960s and 70s, agree that a true mathematical infinity is unlikely to represent physical reality. Instead, many suspect that our current theories simply stop working at that scale, and that a deeper theory, one that successfully merges general relativity with quantum mechanics, would reveal something else entirely, perhaps a region of extremely high but finite density. This deeper theory does not yet exist. Physicists call it quantum gravity, and despite decades of work on candidate approaches, string theory, loop quantum gravity, and others, no experimentally confirmed theory of quantum gravity has been established. This remains one of the biggest open problems in physics. Does time even exist inside a black hole? Here's where things get genuinely strange, even by the standards of this topic. Inside the event horizon, the roles of space and time, in a sense, swap places in the mathematics of general relativity. Falling toward the singularity stops being something you could choose to avoid. It becomes as inevitable as moving forward in time is for us outside the black hole. Some physicists interpret this to mean that inside a black hole, time, as we understand it, stops being a meaningful concept altogether, replaced by a kind of directional inevitability toward the singularity. Others caution that this is more a limitation of the coordinate systems physicists use than a deep truth about reality. This remains an active area of theoretical debate, not a settled fact. The information paradox. There's a second major controversy tangled up with black holes and time, the black hole information paradox, raised prominently by Stephen Hawking in the 1970s. Hawking showed that black holes are not perfectly black. They slowly emit faint radiation, now called Hawking radiation, and over unimaginably long timescales, they can evaporate entirely. But this raised a deep problem. If a black hole eventually disappears, what happens to the information about everything that ever fell into it? Quantum mechanics insists that information cannot simply be destroyed. General relativity's simplest picture suggests it might be. This paradox remains unresolved, though recent theoretical work, including calculations involving what physicists call quantum extremal surfaces, has offered promising, though still debated, hints that information may be preserved after all, encoded in the radiation the black hole emits. This is active research, not settled science. Modern discoveries. Seeing time bend in real time. For most of the 20th century, black holes were purely theoretical. Today, we have direct, extraordinary evidence. The first image of a black hole. In April 2019, the Event Horizon Telescope Collaboration, a network of radio telescopes spanning the globe, effectively creating a telescope the size of Earth, released the first ever direct image of a black hole's shadow, located in the galaxy M87, roughly 55 million light-years away. The image showed a glowing ring of superheated gas surrounding a dark central region, direct visual evidence of the event horizon predicted by Einstein's equations more than a century earlier. In 2022, the same collaboration released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy. These images are, in a very real sense, pictures of time itself grinding to a halt at the edge of an inescapable boundary. Gravitational waves. In September 2015, the LIGO observatory detected gravitational waves for the first time, ripples in spacetime itself, produced by two black holes spiraling into each other and merging over a billion light-years away. This discovery, honored with the 2017 Nobel Prize in Physics, confirmed yet another prediction of general relativity and opened an entirely new way of observing the universe, not with light, but with the vibrations of spacetime itself. Since then, LIGO and its partner observatories have detected dozens of black hole mergers, each one a direct test of how gravity, time, and space behave in the most extreme environments in the universe. The clocks in orbit. Beyond black holes, gravitational time dilation is tested constantly, closer to home. In 1971, physicists Joseph Huffell and Richard Keating flew atomic clocks around the world on commercial airliners and compared them to stationary clocks on the ground. The results matched Einstein's predictions with remarkable precision, a real-world demonstration that time genuinely does pass differently depending on gravity and motion. Modern experiments have pushed this further. In 2010, physicists at the National Institute of Standards and Technology measured a detectable difference in the passage of time between two atomic clocks separated by a height difference of just 1 foot, a direct tabletop demonstration that gravity bends time even across the smallest of scales. Philosophical implications. What this means for us. If time can stretch, slow, and even lose meaning near a black hole, what does that tell us about the nature of time everywhere else? For centuries, humans assumed now was a universal shared moment, that somewhere out there, this exact instant was happening the same way for everyone everywhere. General relativity reveals that this comforting idea is simply not true. There is no universal now. Every observer, depending on their motion and the gravity around them, experiences their own slice of time, slightly out of step with everyone else's. This raises a question that has occupied physicists and philosophers alike, including Roger Penrose himself. If time is relative, flexible, and observer-dependent, is the sense that time flows, that the past is fixed, the future open, and only the present is real, a fundamental feature of the universe, or something our minds construct to make sense of a deeper, more static reality. Some physicists, following Einstein's own later views, lean toward what's sometimes called the block universe idea. Past, present, and future all exist equally, like frames in a film reel, and our sense of time passing is a subjective experience rather than an objective fact about the universe. Others, including some working on quantum gravity and the arrow of time, argue that this view is incomplete, and that something about the universe's expansion and increasing entropy may give time a genuine one-way direction after all. This is not a settled debate. It touches some of the deepest unresolved questions in physics and philosophy, and honest scientists on both sides acknowledge how much remains unknown. What is certain is this. The moment you accept that gravity can bend time, you have to give up the comfortable idea that reality unfolds the same way for everyone, everywhere, all at once. The universe does not run on a single clock. It runs on billions of slightly different clocks, each shaped by the mass and motion around it, including, quite literally, the clock on your own wrist, ticking at a rate found nowhere else in the universe. Ending. Somewhere out there, at the edge of a black hole, a clock is still falling. From our point of view, it will always be falling, frozen at the boundary, its final tick stretched out toward infinity, never quite completing, and yet, in its own reality, that fall already happened, long ago, instantly, completely. Two truths, both real, both mathematically confirmed, existing at the same time, or perhaps more accurately, existing at completely different times, depending entirely on where you happen to be standing in the universe. Maybe that's the real lesson hiding inside all of this. We like to think of time as the one thing in the universe we can always count on, steady, universal, the same for everyone. But the deeper physicists have looked, from Einstein's beam of light to the shadow of a black hole 55 million light-years away, the less that comforting idea seems to hold up. The deeper we look into the universe, the more it begins to look back at us,